Hello everybody, my name is eMoney Esedi. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 18. Now in this chapter we are going to learn how reactions with aromatic compounds work. We're going to learn 7 main reactions, and as we go through this chapter we're going to elaborate on each single reaction in a more critical way. We will also understand how monosubstituted reactions proceed, and we will eventually understand how to work with these reactions when our benzene ring is multi-substituted. Now, in these 7 reactions that you observe here on this page, we see an electrophilic aromatic substitution reaction in which one of these aromatic protons is replaced by an electrophile, all without ruining the aromaticity of the ring in the final product. Now we're going to create little profiles for each one of these reactions, starting with halogenation reactions of benzene, and we're going to first talk about bromination of benzene. Now the goal for this reaction is to add bromine to the ring, and in order to do that we can use either one of these reagents we have listed here. Now, in the mechanism of this reaction, we first form a catalyst, and it is this catalyst complex that serves as an electrophilic agent that pretty much initiates and achieves bromination of the aromatic ring. When the aromatic ring attacks the catalyst, because remember, our double bond in our aromatic ring acts as the nucleophile, and our first step is a nucleophilic attack, where our double bond is going to attack our electrophilic reagent. We form this positively charged intermediate that we call the sigma complex. Now, the consequence of forming this sigma complex is obviously the loss of aromatic stability. So this step actually requires a lot of energy. But no worries, because our last step is a proton transfer that reforms an aromatic product, which is very stable. Now, the thing that you want to compare this to and keep in mind is you've seen an addition reaction in chapter 18 of your Organic Chemistry 1, where we halogenate a pi bond. All right, say this is Br2, we add bromine to both sides of the aromatic ring. Please note that addition reactions like this are not seen with aromatic compounds like benzene, because it results in the loss of aromaticity, and that's extremely unfavorable. Now, like with bromination of benzene, we can also see chlorination of benzene, where our goal is to add chlorine to the aromatic ring. All right, the reagents that we can use to do this are listed here. All right, and the reaction mechanism is actually very similar to bromine. The main difference is, of course, our catalyst complex here. Our catalyst complex for adding chlorine to the benzene ring looks like this, as opposed to the complex for bromine, which was a little different. Of course, again, our first step is a nucleophilic attack. We form this sigma complex intermediate. All right, and with our last step of a proton transfer, the sigma complex is deprotonated, and we restore aromaticity in our final product. Again, iodination of our benzene ring, where we want to add iodine to our aromatic ring, is also very similar to bromination and chlorination. The reagent we use here is listed. All right, and now the mechanism for this reaction is again also very similar to the two we listed before, with the main difference being what our catalyst complex looks like. First step is nucleophilic attack. All right, again, we form a sigma complex, and our sigma complex is again deprotonated to restore aromaticity in our final product. Now, most Organic 2 classes require that you become not only familiar with the reaction mechanisms for these aromatic electrophilic substitution reactions, but that you memorize the mechanisms as well. So if that is something your professor requires, make sure you learn and memorize these reactions by drawing them over and over again. That's usually the best way to learn, as well as doing practice problems. And we're going to get to several practice problems here in a little bit. Now, the next reaction we want to cover is sulfonation of benzene. All right, when benzene is treated with fuming sulfuric acid, all right, you get to add sulfur trioxide to your benzene ring. Now, the reaction mechanism for this involves a nucleophilic attack and a proton transfer. Again, this sounds super familiar, right? Well, spoiler alert, this is because this is characteristic of pretty much all electrophilic aromatic substitution reactions. Now, let's look at this reaction mechanism a little closer, right? Our first step is nucleophilic attack, where our aromatic ring functions as a nucleophile, attacks our sulfuric acid, and forms an intermediate sigma complex. All right. Now, the last step is this last few steps are proton transfers, all right, where the sigma complex is once again deprotonated, restoring aromaticity, and then finally the resulting anion here is protonated to form our final product, where we add this sulfur trioxide to our benzene ring. All right, now, one quick thing to remember is if you are trying to do an aromatic electrophilic substitution where you add our sulfur trioxide to our benzene ring, you use fuming sulfuric acid. However, if you are trying to accomplish the reverse reaction, what you would want to use as a reagent is dilute sulfuric acid. So that's a good thing to keep in mind for future synthesis problems as well. Now, the next reaction we want to do is nitration reactions. The goal here is to add an NO2 group to our aromatic ring. To accomplish this, all right, these reactions occur with a mix of nitric acid and sulfuric acid. The electrophilic reagent is actually formed from these two acids. To restate, this reaction proceeds via an electrophilic aromatic substitution in which a nitronium ion is believed to be the electrophile. This strong electrophile is formed from the acid-base reaction that takes place between nitric acid and sulfuric acid, as you see here. Nitric acid functions as a base to accept a proton from sulfuric acid, followed by the loss of water to produce this nitronium ion. Now, once on the ring, then the reaction mechanism, again, very similar. Nucleophilic attack that forms a sigma complex, and our aromaticity is restored via a proton transfer at the end. Now, there is more that you can do with this, actually. I think this is very cool. Once you have the nitro group on the ring, you can further reduce it to give an amino group right here. And you can accomplish this using any set of these reagents listed here. All right, any one of these reagents can accomplish this reduction where you can convert your nitro group to this amino group here. Fantastic. This is also going to be really useful for future synthesis problems. So make sure that you remember this. Now what we want to talk about is Friedels alkylation. Now, this reaction adds an alkyl group to our benzene structure, and it's made possible with this set of reagents. All right, now our aluminum trichloride is very important here. This reaction is made possible with aluminum trichloride. It's important because it converts whatever alkyl group we are trying to add to our ring to a carbocation. All right, now the result here, of course, with our aluminum trichloride is the formation of a carbocation. And this carbocation is going to be an excellent electrophile, and it's going to be capable of reacting with benzene via an electrophilic aromatic substitution reaction. Now, you can see how that occurs, right? We have this alkyl group that we want to add to our ring. Of course, it has a leaving group, and this reacts with our aluminum trichloride to form a carbocation of the alkyl group that we want to attach to our benzene ring. Now, the result here, this formation of a carbocation, is an excellent electrophile. After the formation of the carbocation, two steps are involved in the electrophilic aromatic substitution. In the first step, the aromatic ring functions as a nucleophile and attacks the carbocation, right? Nucleophilic attack, again, to form a sigma complex. Now, the sigma complex here is then deprotonated in our last proton transfer step to restore aromaticity. All right, and that's the reaction mechanisms for this. Now, some things to keep in mind here. All right, our alkyl halide is converted into a carbocation, which means that carbocation rearrangement is possible. All right, sometimes carbocation rearrangement here can be possible. All right, so of course, when this happens, the major product is formed from the more substituted carbocation, from the more stable carbocation. Now, the requirements for this reaction is usually a secondary or tertiary alkyl halide. Sometimes you'll see it is possible with primary alkyl halides. Of course, what we're predominantly going to see here is secondary and tertiary alkyl halides. The limitations, of course, that we have to keep in mind. All right, with Friedels alkylation, there are three things we want to keep in mind. One, when what alkyl halide can participate in this reaction? Well, an alkyl halide where the carbon atom connected to the halogen is sp3 hybridized. So when choosing an alkyl halide, the carbon connected to the halogen has to be sp3 hybridized. All right, now polyalkylation happens because adding one group in the ring can activate it for further alkylation. So installation of alkyl groups sometimes activates the ring toward further alkylation. That's something that's very important to keep in mind. Now, some groups, when they are present on the benzene ring, can prevent further Friedels alkylation from happening. This is an important point that will reappear when we do some synthesis problems later on. Fantastic. Now, we want to move on to Friedels acylation. For Friedels acylation, just like alkylation, we can add acyl groups, and it's possible through a very similar method. An acyl chloride is treated with a Lewis acid to form a cationic species called an acylium ion. Sorry, I'm going to write that because I cannot pronounce it very well. An acylium ion. All right, so we can see that here in this first step. This is our acylium ion. Fantastic. All right, so let's look at this mechanism. Very similar to Friedels alkylation. We first have our nucleophilic attack, all right, to form this sigma complex that is eventually deprotonated via a proton transfer to restore aromaticity. Now, the product of Friedels acylation is this aryl ketone, which is very important, all right, and can be again produced with the use of aluminum trichloride, which is used in this first step to form our acylium ion. Now, when you have your product for Friedels acylation, it can actually be reduced further. It can be reduced using a Clemson reduction. All right, in the presence of hydrochloric acid and amalgamated zinc, all right, the carbonyl group here is completely reduced and replaced with 2 hydrogen atoms. All right, so this is very important. You can proceed with a Friedels isolation where you add an acyl halide, an acyl halide, I'm so sorry, to an aromatic ring through the use of aluminum trichloride, where our acyl chloride is treated with this Lewis acid to form our acylium ion. All right, where we get at the end of this an aryl ketone attached to, of course, our benzene ring. What we can further do is reduce it using these reagents. Again, this is going to be very important for synthesis problems that we are going to do later. Now, something to note here is polyacylation is not observed, right? Because introduction of an acyl group is gonna deactivate the ring towards further acylation. This is different than Friedels alkylation. Again, something here to note, there's not gonna be any carbocation rearrangement, so you do not have to worry about that here. Now, of course, the best way to make sure we understand all 7 of these reactions that we have covered, let's jump into some practice problems. All right. This first practice problem states, which of the following statements is incorrect? A states that an aromatic compound loses its aromaticity in the first step of an electrophilic aromatic substitution reaction. This is correct statement. We do lose aromaticity. Our first step in these reactions is a nucleophilic attack that results in the formation of a sigma complex where aromaticity is lost. This statement is correct. B says benzene requires a strong electrophile in order to undergo an electrophilic aromatic substitution reaction. This is also a correct statement. We need a strong electrophile. All right. C says the rate determining step of our electrophilic aromatic substitution reactions is the exothermic removal of a proton from sp3 carbon. So our electrophilic aromatic substitution reactions have 2 major steps: nucleophilic attack and then proton transfer. This answer choice says that our proton transfer is our rate determining step. This is actually incorrect. Our rate determining step is our first step where our nucleophilic attack occurs. All right, so this is our rate determining step. This means that the statement that is wrong here is statement C. All right, fantastic. Now, this question says, which of the following species is attacked by benzene in an electrophilic nitration reaction? All right, the species that is attacked by benzene in an electrophilic nitration reaction is actually NO2 plus. All right, so this is answer choice B. All right, now our next question says fill in the boxes with suitable compounds. All right, so what do we start off with that we can treat with these reagents to form this product? All right, this is a simple bromination of benzene, which means our starting material is benzene. We can treat benzene with the following reagents to form this product. This is called bromination of benzene. All right, now what if we have a benzene ring that we treat with this reagent? All right, this is iodination of benzene, and what we do here is simply add an iodine group to our benzene ring. So this is what our product will look like. Now, for this last set of this last reaction, we have a benzene ring. We want to add a chlorine group, right? So this is chlorination of benzene. What kind of reagent can we use here? We could do Cl2 along with aluminum trichloride to chlorinate our benzene ring. All right, so these are a good set of reactions that help us reaffirm our halogenation reactions of benzene. All right, let's move on to a next question. Which reaction conditions facilitate an electrophilic aromatic substitution reaction? All right, so this is good to make sure that we understand which one of these are actual reagents used in electrophilic aromatic substitution reactions. This first set of reagents is not used in any of the 7 reactions we learned in, nor is B. All right, C, however, we do see for chlorination of benzene. So this is actually a reaction condition that is used to facilitate electrophilic aromatic substitution reactions. D is not seen in these types of reactions, nor is E. So the only correct answer here is C. All right, fantastic. Let's do some more aromatic electrophilic substitution reactions. All right, so A, we start off with a benzene and we treat with these reagents. This is chlorination of benzene. That means that our product will look like this, where we add a chlorine group to our benzene ring. All right, this next reaction, these reagents, when treated with a benzene, all right, is our nitration reaction. So we can add a nitro group to our benzene ring. So our product will look like this. All right, then we have this reaction. These reagents indicate sulfonation of benzene ring, where we add sulfur trioxide to our benzene ring. Fantastic. All right, next we want to show how each compound can be synthesized from benzene by using acylation reduction. All right, fantastic. So if we want to add a group to our benzene ring through acylation, all right, Friedel-Crafts acylation, and then as a last step, we want to figure out how we can reduce it to get this final product. If we have any room to draw this here, we don't. Let me fix this. All right, so we're trying to figure out how we can conduct Friedel-Crafts acylation here, and then take this product and through acylation reduction get this final product we see here. So what would we have to treat our benzene ring to get something that looks like this? All right, that's the goal here, so that we can then reduce it to get this. All right, so our first set of reagents that we need, all right, is going to be something that looks like this. Exactly the acyl group that we want to add with a halogen attached. That's going to serve to be our leaving group, plus aluminum trichloride. All right, so for this first set of reaction, this Friedel-Crafts acylation, all right, where we add this acyl group here, all right, the reagents that we need are this group and aluminum trichloride. Now, what we want to do with this product is then reduce it. All right, reduce it to form this final product. Now, one set of reagent that we can use to reduce our Friedel-Crafts acylation products is zinc and hydrochloric acid with some heat. So this is the set of reagents that we will need to do reaction A. All right, and they specifically say that they want us to first produce our Friedel-Crafts acylation product and then reduce it. All right, let's do B. All right, again, we want to go through our Friedel-Crafts acylation to get a product, all right, that looks like this product but with a carbonyl group. All right, with a carbonyl group. And then reduce this to get this final product. So for this first step, the set of reagents we are going to need look like this. Let me draw this properly. with a, and then add a halogen group here. That's gonna serve as some leaving group, and aluminum trichloride. So we treat benzene ring with these reagents to get this product right here. All right, through Friedels Isolation, we get this product right here. Now, this is not the last step. We want to reduce this final product so that we get this. All right, how do we do this? Again, same list of reagents that we can use to do this reduction is zinc, hydrochloric acid, and heat. All right, fantastic. Now, I will leave C for you to try and figure out. And what we're going to do is we're going to move on to this set of problems right here. Now, if we take this benzene ring and treat it with this set of reagents, what kind of products are we going to get? Well, what we realize is the reagents we have here are going to result in a Friedels alkylation. And the first step is going to be to form this carbocation right here where this chlorine group leaves. All right, and so we form this carbocation. Now, an important thing to note here, all right, this group, this carbocation can also go through carbocation rearrangement, and through carbocation rearrangement, we can have this carbocation as well. So both of these carbocations, all right, this hydrogen can shift over here through a hydride shift to form this. Now we have these two carbocations that are going to result in two different products from this reaction. One product is going to look like this, all right, and one product is going to look like this. All right, it's important to notice that for Friedels alkylation, through this first step of forming a carbocation, to stop, pause, ask yourself, can carbocation rearrangement happen? And if it can, make note of what that carbocation looks like, because both of these carbocations are going to result in products. And these two products are the products of this reaction. All right, make sure to note this. All right, fantastic. So for this reaction, we form these two products. Our major product is going to come from the more substituted carbocation, which is this one. This is a primary, this is secondary. The product that is formed from our secondary carbocation is our major product. Fantastic. I am going to leave B and C for you to attempt. And of course, if you have any troubles, I will post the answers. We're going to move to this last set of reactions before we end the session. All right, we have this benzene ring, and we're going to treat it with these two reagents. All right, this looks like a Friedels Isolation. All right, so we know what happens here. All right, we are going to pretty much, in short, attach this group right here, all right, to our benzene ring. All right, we're going to be attaching this group to our benzene ring. And the product that this is going to give us will look like this. Wow, that is so bad. Let me fix that. There we go. That is better. I'm so bad at drawing these. All right, so we know this is a Friedels Isolation. All right, we have this group along with aluminum trichloride. We know that what we're going to add is this aryl group to our benzene ring minus the leaving group that we have here, this halogen. All right, so we're just going to go ahead and attach this to our benzene ring. Same goes for B. All right, this is again a Friedels Isolation, and what happens is we're going to add this group minus the chlorine to our benzene ring to give us a product that looks like this. All right, these are all the practice problems for this. I hope this was helpful. Next time, we're going to cover how to deal with monosubstituted benzenes in terms of reactions and how those will proceed. All right, and we're going to do lots more practice problems as we go through chapter 18. I hope this was helpful. Good luck and happy studying.